Thank you, and I'd like to thank the organizers again for this opportunity to be here and to give a talk about some work that we will put out early next week. I'd also like to advertise some work from our friends, which will appear on the same day, hopefully. And they have very closely related results and very interesting analysis of solutions in the Landau-Ginzburg model. And whenever I mention exciting results from our behalf, I'll try to advertise what they find as well without going into too much detail. Okay, so the main takeaways from this talk is that we are able to find what we believe are some of the first examples of fully stabilized 4D n=1 Minkowski vacua in string theory. And another interesting takeaway is that we're able to violate the refined version of the tadpole conjecture for the type 2B, the type 2B version of the refined tadpole conjecture. And both these results are also found in the companion paper that I advertised in the previous slide. Okay, now let me briefly mention the plan for this talk. I'll begin by motivating a bit what we're doing, and then I'll review the models that we're studying, and then tell you about our results and end with a summary. Okay, so let me begin the motivation. So as we heard in Sav's talk yesterday, moduli stabilization and finding string vacua are very, very difficult problems, and this still remains a main obstacle to finding string models that describe our real world. And with the Swampland program, we hope that the criteria that we find would give us some way to characterize these obstacles. And they give us sharp quantitative bounds that we can actually test in constructions. And patterns that we observe have been studied extensively in asymptotic limits of moduli space, but it's a very useful question, an important question to ask if they actually hold in the interior of moduli space. And this is slightly what we're trying to do. And the non-geometric models that I will discuss today have already provided novel testing grounds for many Swampland criteria. For example, a couple of years ago, with Tim, Eduardo Gonzalo, and Tim's other students, we checked the ADS distance conjecture in these settings. Recently, last year, we also studied the possibility of engineering asymptotic acceleration from these non-geometric models. And recently, we've been thinking about the tadpole conjecture in these settings. We put out a paper last month on the 1 to the 9 model, and now we're working on the 2 to the 6. But let me first explicitly mention two Swampland criteria that are most interesting to the work that we're doing right now. So David, who was here yesterday, along with collaborators, has this conjecture about Minkowski vacua always coming with massless scalar fields. Now, strictly, this doesn't apply to these cases that we're studying because we don't have a 10D supergravity description. So you could naively say that even if you find solutions with no massless scalars in these models, it doesn't necessarily violate this conjecture. And several people, of course, have worked on constructing Minkowski vacua. This list is not exhaustive, so I apologize if I miss anyone. And the other conjecture where, sorry, it got cut off for some reason, but the other conjecture, which is stated here very roughly, very qualitatively, is that the number of moduli stabilized by fluxes is sort of constrained by this relationship. So the point is that the flux contribution of the tadpole, the contribution of the fluxes to the tadpole grows in an undesirable rate for moduli stabilization. This bound is 1/3. So this strictly is the refined tadpole conjecture. The original tadpole conjecture only predicts a linear relationship between these, and this is spectacularly like verified even in non-geometric settings. But the 1/3 is the refined tadpole conjecture. And let me also clarify what I mean by stabilized fields here. You can take this to mean the massive field, so you can ask what the Hessian of the superpotential is around the critical point, but you could also allow for fields that are not massive, but are stabilized. So a term like 5 to the 4 without phi square would have a critical point that's isolated at phi = 0, but would not have a mass term per se. And of course, the number of massive fields are contained in the number of stabilized fields. And in this work, we're able to test the conjecture in both these forms. You can also ask if it holds at the level of the mass matrix rank, but you can also go a step further and ask if things that are not massless are indeed flat. And the philosophy here is to sort of use explicit string constructions to inform Swampland conjectures. So the real philosophy is that they were never really fighting, but they were always friends, right? Some of them, I guess, okay. I didn't say that. Okay, so now I can maybe move on to the review of Landau-Ginzburg models. I'll try to be brief here and try to go slightly quick, but please do stop me, or I'm happy to discuss the details later. If you decouple for the next 10 minutes, I'll tell you where you have to decouple to then understand our results. Okay, let's get started. So it was shown by these authors that we could potentially stabilize all moduli in type 2A when you compactify on a rigid Calabi-Yau. There are potential issues maybe that Sav raised, but this is not important for this talk. I'm mentioning this more for like chronological motivation. Motivated by these results, Becker, Waffa, Walcher tried to ask what the mirror dual is in type 2b. So if you naively just think about this, mirror duality switches the number of complex structure to the Kähler moduli. So a rigid Calabi-Yau with no complex structure would get mapped to something with H11 equals 0, which is not even Kähler. But it turns out there is a Landau-Ginzburg description, an SCFT description, which will still save us, even though we don't have a Kähler manifold description. And naively, these models would suggest that you don't have the problem of volume stabilization, right? But I'll point out later that it's still not that easy to stabilize the complex structure and the axial dilaton. But at least naively, the problem that KKLT faces and so on is evaded here from the get-go. And how is this okay? Well, string theory never asked us for geometric compactifications or for geometric backgrounds. It only asks us that we have the right central charge of the internal CFT to get a consistent theory. And an internal CFT with the right central charge does not always correspond to a geometric manifold. Right? For example, consider this Landau-Ginzburg theory, where the X size are chiral superfields and the superpotential is quasi-homogeneous. This theory in the IR flows to a Gepner model, which is a CFT. And these could also provide consistent string backgrounds for us to compactify on. So let's first look at a minimal model, which is an N equals 2 CFT, which has this kind of superpotential. It has the following central charge. This is known as a level K minimal model, and it has the following central charge. This by itself would not give us a consistent string background because we need C equals 9 for the internal CFT. So for example, if you take K equals 2, you get the level 2 minimal model with the following central charge. But you can tensor together 6 copies of them, and you end up with the right central charge for a string background. And in principle, you also have to perform this orbifold, which projects you onto integral U1 charges to have the right space-time supersymmetry. And you can also ask what happens if you tensor together, what happens if you study the level 1 minimal model, which again has the central charge of 1, which is not sufficient, but you can tensor together 9 of these and get the right central charge. So these are the 2 models that we will study. The 2 to the 6 here, which are 6 copies of the level 2 minimal model, and the 1 to the 9, which are 9 copies of the level 1 minimal model. Yeah. They admit deformations, but I don't think, I would say they live in the Kähler moduli space of the would-be mirror dual to a rigid Calabi-Yau. I wouldn't call them Calabi-Yaus by themselves. I think so. I think it only exists at the Landau-Ginzburg point. And right, this is dual to the rigid one, that's right. Yeah, it's not Calabi-Yau. Yeah. Right. Yeah. Okay. So just to build some intuition or maybe some machinery so that we can study space-time physics, which is what we eventually want to do here, let me break down the 2 to the 6 into its minimal model, which is just the level 2 minimal model. One can ask what the equivalent analog of A branes are in these settings, because we'd like to understand how to study fluxes and D branes and ask what cycles these fluxes can wrap. And it was shown by Kumrun and collaborators many years ago that for such a simple superpotential, that the A branes are given by the vanishing locus of the imaginary part. And these are not all independent. They're related by this relation here. And to get the right A branes for the 2 to the 6 model, in principle, I have to tensor together 6 copies of these, and this can be done. And to be completely right, if you want to get the integral homology, you also have to divide out by the Z4 symmetry that you have. And you can study the Poincare duals to these cycles and write down what forms are. Now, if I'm going too quick or saying things that don't make sense, it doesn't really matter what I'm saying here. What matters is that you take home the message that there is a consistent way to write down what a form is, what a notion of a form is, and I can turn on fluxes that couple to these forms. Yes, in this basis, this is an integral homology. These n's and m's are integers, yes. But very quickly move on to another basis where they're not quantized, but there is a map that can bring us to this quantized basis. I'll mention this now. So we can also study the Raman-Raman downstates of the minimal model, which for the 2 to the 6 are given here. And these by spectral flow are related to the chiral ring of the superpotential. Again, not very important. The bottom line is, if you can tensor together 6 copies of these ground states, I can give you another basis for studying forms in this language. So for example, a H2,1 form would have these kind of structures. So you can either have 2 1s and 4 2s and other permutations of this. You can have 3 1s, 2 2s, and a 3, and other permutations of this. You can have 4 1s and 2 3s and other permutations of this, and this also provides for you a basis. And I'll call this the omega basis. And it's not flux quantized. The flux there is no notion to turning on a flux in this. Like if I tell you that I turn on a flux of this nature here, it doesn't necessarily mean anything physically. But there is a transformation to go from this basis to the flux quantized basis I showed before. And I'll mention this in a moment. A similar game can be played for the 1 to the 9. Again, not very important, but for the 1 to the 9, just one thing I'd like to bring your attention to is the number of options we have for H2,1 forms reduces. And this is just an artifact of the superpotential. So here we had 3 options for the forms that would be in H2,1. Here we only have 1 option, and this will be important later. Okay, bottom line is we have 2 bases to write down what forms are in these models. One is given by the Raman-Raman downstates of the CFT, and this comes from the integral homology. In this basis, things are quantized, and there is a map to go from here to here. I will work primarily in this basis, but will always check that when I go to this basis, the fluxes are quantized. And what are the moduli in these models? The 2 to the 6 has actually 90 complex structure and no Kähler moduli. And what we'd like to study is n equals 1 physics. So right now we're only at n equals 2. So we'd like to study orientifolds of these models. And the orientifold is generated by this involution, which was studied and worked out in this paper from Kumrun and collaborators. And I'm just going to state here that it has a charge of 40. So the tadpole that we need to cancel is 40. And similarly for the 1 to the 9, we start out with 84 complex structure moduli and no Kähler moduli. Choose this orientifold, which has a charge of 12. So this is the charge that has to be cancelled by fluxes. But here the orientifold also projects out some complex structure moduli. So you end up with 63 complex structure and the axiodilaton and no Kähler moduli. Okay. You can actually check the deformations that are H2,1, there are 84 of them if you do the permutation counting of those. That's right. I'm only writing on the H2,1. There are other 3 cycles that you can write in the same language. I'm just not writing them. That was more in the omega basis, the kinds of forms that I can write down that would be in H2,1. There are still 84 of them, that's right. There are still many. I'm not saying that the number of 3 forms reduces. I'm saying that the kinds of options, this variety in the kind of 3 forms you can write down, written in this basis. Right. Or 90. Right. I'm saying that they can be classified into different types written in the omega basis. And this seems to be important. This seems to give us more freedom to stabilize more moduli and so on. It's just an observation. There's nothing deep or anything that I have to say there. And the moduli are the marginal deformations of this world sheet superpotential. So you can actually count that there are 90 of these, like you were saying, coming from what the 3 forms are. Again, if you decouple, the relevant information is in this slide. The point is, for the 2 to the 6 Landau-Ginzburg model, there are 90 plus 1 moduli. So 90 complex structure, 1 axiodilaton, no Kähler moduli. And the tadpole charge you want to cancel of the orientifold we're studying is 40. For the 1 to the 9, there are 63 complex structure and 1 axiodilaton. And the tadpole charge you want to cancel is 12. And of course, both of them have no Kähler moduli. And this overlap integral between the cycles and the Raman-Raman ground state is important. It's not important that you digest this, but this will let us compute the analog of integrating a 3-form flux over a 3 cycle, essentially, when generalized to the tensor product theory. And you can also ask, if I allow for deformations about the superpotential, what the derivatives are at this Landau-Ginzburg point of the superpotential, right? So deformations of the minimal model really have no meaning. There's no geometric analog of a moduli there. But for the tensor product theory, there is actually exact marginal deformations we can study. And so we can take derivatives with respect to moduli of the superpotential at the critical point. I'll again come back to this point when it's necessary. But the point is this is computable, and this is very important for our analysis. If there are any questions, I can answer them right now. If not, move on. Okay, yeah. Right. Well, we're not doing a supergravity analysis, but I agree that once you run on fluxes, you deform the CFT. You have a CFT description, you deform the CFT. So I'll mention this in the end as a potential caveat to these solutions, but this is completely right. We don't know if it still remains a CFT. We don't know how to study it, or we haven't studied it. I don't know. There is no problem with smearing and so on, I would say here, I think. Okay. Okay. So the bottom line is there is a Gukov buffer within superpotential, right? There are non-geometric analogs to all the things that go into computing this formula for the Landau-Ginzburg models as well. And the real kicker is the superpotential is actually non-perturbatively exact as well. This is the claim, at least. For example, there are no force cycles here. So Euclidean D3 Brane instantons, which would typically contribute to the superpotential, don't contribute here. And this is very important for us because we'll be working at order 1 string coupling. And so in principle, if they were there, they would destroy our solutions. But there's a non-denormalization theorem that goes back to these authors. And there is some extra evidence from Mankey-Kim's calculation that D-1 instantons also don't really affect the superpotential here. No, there are no force cycles. There are no 7-brane moduli. That's what you were asking. And that's sort of why I'm pointing out Mankey's work as hint, because this is what he found. The 7-brane charges have to cancel locally for the D-1 instanton contributions to vanish exactly. And this is, yeah, I mean, I'm hand waving a bit here, but yeah. Yeah. As in the deformations that I showed of the world sheet superpotential? Here, this? Yeah. I mean, this is not really a marginal deformation or anything of the superpotential. I'm doing this as a trick. The actual right thing to do is to take the full superpotential of the 2 to the 6, and there you have exact marginal deformations, and you can construct a similar formula. It doesn't necessarily easily fit on this slide, so I cheat a bit here. Actually, I don't have a concrete explanation for this, except that Mankey finds in a calculation of a toroidal orientofold that when the 7-brane charges cancel locally, they're not there. This is morally a toroidal orientofold. You can think of it as a quantum orbifold of some, yeah. So yeah, I don't have any concrete computations to show that. All right. So just to remind you of the targets again, in the 1 to the 9, you have a tadpole of 12. If you believe the 1 by 3 bound to the tadpole conjecture, it tells you can only stabilize 36, and there are 64 in total. So if you believe the tadpole conjecture, you would never stabilize everything. In the 2 to the 6, the tadpole charge is 40, which the tadpole conjecture would tell you could stabilize 120 fields, and there are only 91. So if you were to find an example here, you wouldn't really contradict the tadpole conjecture or the refined version. All right. So now keeping these numbers in mind, which I'll keep reminding you, I'd like to show you some of the results that we have. Doing decently on time. Okay. And before I do that, let me first explain the strategy for what we're going to do. So all the formulas I showed you there at the Landau-Ginzburg point. So we can compute these overlap integrals, derivatives of these overlap integrals, and so on only at this point. So what we will try to do is find critical points and do an analysis of what the rank of the deformation space of this critical point is once you have the critical point. So let me start with the toy example. Just consider this function. This is not related to any of our real examples, but just an example with two fields. Clearly, this function has a flat direction along phi equal to psi square, right? So let me now try to explain to you what we do order by order to lift fields or to understand whether there are flat directions. I'll first start at quadratic order, right, where the superpotential is just half phi square. If I ask what dw equals 0 gives me, it tells me that phi is 0, right? Now if I say, okay, now let me go to cubic order in the fields, I also get this extra term. Now again, I want to study the critical point equations. And this naively tells me that I fixed two fields, right? Because there are two constraints I get. But I already know that there's a flat direction in this function. So where am I going wrong? It's because I'm doing something completely stupid. I'm forgetting that I'm doing perturbation theory. So at quadratic order, we solve the non-trivial critical point equation to fix the field at linear order in the other fields. Right? I haven't fixed this field phi to be 0 at all orders in the other fields. Sorry, yes, sorry, thank you. There's a plus missing here. And if I keep that in mind and truncate at the right order, I will still get this one non-trivial constraint, but the other constraint will trivially vanish. And so this is all consistent. This tells me that now phi is set to psi square, and that psi is still an unfixed direction, which is consistent with the picture that this function actually has a flat direction. And you can run this algorithm to order 4 in the fields, at which point the superpotential truncates, and you will still find the same result. Of course, this is totally redundant for such a simple function. Why would I do this? It's because we don't know the full function in the superpotential that we're going to deal with. But we know the critical point, and we can compute its derivatives at the critical point. So I can do a Taylor series expansion about the critical point and play this game order by order. In the effective field theory. But those who tell me the isolated critical, or if there are critical points of the world sheet superpotential, right? Right. Yeah. Right. Okay. I mean, this is exactly what we're doing. We don't have an effective supergravity description. This is when I'm saying I'm computing a superpotential and taking its derivatives, it's in that language. Yes. So it's supersymmetric. Yes, it's supersymmetric Minkowski. No, we have to choose the fluxes appropriately for that. If the fluxes fall in H2, 1, which you can show, then you get W equals 0 vacua. In principle, you could get W not equals 0 vacua as well. But the Caleb. No, we're not turning on a 3-0 component. We could, but the Caleb potential gets corrections, and we don't understand it. So, yes. Yes, it's the point where the model flows to a Gepner model. No, I would say we're already at the CFT point at the world sheet level. That's how we even start doing these computations. Order by order, this is an expansion in the space-time superpotential. Yes, but the superpotential is. Sorry, I mean, in the world sheet, we are at a fixed point, I would say. That's where the Gepner model exists. And we're trying to understand, once you find the critical point of the space-time superpotential, what the nature of the critical point is. I don't know this. Yeah, I guess you can see it as deformations about the fixed point of the world sheet as well. Yes. Yeah, I agree. This I agree with. Yeah, this I agree with. I was. Yes. Yes, that's right. Okay. So now let's actually start doing it in some real examples. First, I'll focus on the 2 to the 6. So picking a W equals 0 vacua in the omega basis amounts to picking an omega with the L summing up to 10, of which there are 3 options, like I showed before. But this doesn't necessarily give you a good string vacuum. because it's not clear that the fluxes are quantized when you turn on one omega unit of flux. But you can check this, and this is the process of finding Muthusamy-Minkowski vacua in these models. And you also have to ensure tadpole cancellation, of course. So in the 2 to the 6 as well, the generic result is that there are massless directions typically when you do this, when you perform both these steps, so that you actually have a supersymmetric Minkowski critical point. And we don't pursue a classification of these solutions, but this will be done or is pursued in this upcoming work from our friends. I think it's a solution. Yeah. Yeah. Around it, right, exactly. Exactly, yeah. In fact, this guarantees that it's a solution at this point. I mean, that's a non-trivial step. Once I start turning on 2,1 fluxes in this language, it's a bit non-trivial. It's not guaranteed that they're flux quantized. But we check this explicitly at the t equals 0 point. Yeah, at that point, yeah, exactly. Yeah. Okay. And we'd like to play the game that we played before. So for that, we need to compute these derivatives of the superpotential at this critical point. The problem now is I can't give you like a closed form of the full function, right, up to arbitrary order. But what I can give you is that this is a critical point and that you can perform these derivatives at this critical point. So I can sort of rebuild the function if you wish. And for the 1 to the 9, similarly, the condition changes a bit, but the philosophy remains the same. Right? And here also we've observed that there are generically massless directions when you find Muthusamy-Minkowski critical points. This was observed already 2 years ago by Tim and collaborators. So first, I'll review some results in the 1 to the 9 paper that we put out last month. And then I'll show you some more exciting results in the 2 to the 6. The 1 to the 9 is a bit hopeless, but we'll see that now. So again, a very vast classification of flux choices was pursued late last year by our collaborators. And let me try to morally explain how one does this. So you cheat and you stay in this omega basis where there is no real meaning of what a flux is. You turn on 1 unit of omega flux, right? Naively, you have 63 permutation choices for things that are in H2,1, like I was saying. But there are permutation symmetries that reduce you down to just 2 options. But if you check the flux contribution, it's 27. And as you have up here, this is much greater than 12. So these are not physical solutions. Right? So you say, okay, let me turn on 2 units of omega flux, check that they're flux quantized, and ask what the n flux is. It's again still too large to form a physical solution. And you can keep playing this game and realize that you need to turn on at least 4 omegas to get a physical solution with n flux equals 12. And in fact, it was proved in this paper that you can only turn on up to 12 omegas because each omega contributes 1 unit of n flux. So if you turn on more than 12, then you're reaching the tadpole bound. A very intriguing point about this is in the omega basis, you can either turn on 4, 8, or 12 fluxes. You can't turn on anything else to get a physical solution. We don't understand why this happens. We tried mapping this to the underlying symmetries of the Gepner model. It doesn't seem to follow from any of this, or maybe we're missing something. And you can play this game, keep going, and generate a vast list of solutions and ask what their n flux is and what the mass matrix rank is of these critical points. And we did this in this recent paper. And this red line is the tadpole conjecture bound, the 1/3 bound. And as you can see, this is a pretty spectacular verification of this conjecture. But what we really wanted to study in this was to ask, are massless modes actually flat directions, right? You don't have to necessarily stop here. The number of stabilized fields are not equal to the number of massive fields. You could still lift a massless direction. So for this, I again flash this formula where you can compute derivatives of the superpotential at the critical point. Not very critical. Point is if I turn on 1 unit of omega flux, I have a nice formula like this that tells me some rth derivative that I'm taking with respect to the moduli at this critical point. So I can do this Taylor series expansion of this critical point. Right? And what we find is summarized in this table. So for the moment, you can ignore all these things in the first column. They represent different flux choices. And even though it looks like we're studying just a finite number of flux choices, they have big degeneracies, and they actually represent a vast number of solutions that are there in the 1 to the 9 Landau-Ginzburg model. So we do a pretty close to exhaustive analysis. What we find is that generically, nothing gets lifted even if you go to higher orders. So for example, you have started with 14 massive fields for this flux configuration. You find none get lifted at cubic, none get lifted at quartic, and so on and so forth. Right? But there are examples where you can at least have a proof of principle that massless directions are not necessarily flat. So for example, you start with this flux configuration, which gives you 16 massive fields. You can lift 6 at cubic order, then it falls off. There are slightly more exciting results where you can lift 7 and then 4 at quartic order, and then it falls off. And the question mark is a point where we can't do any computations anymore, just because of our capabilities. And the table also truncates here for the same reason. In principle, we can keep computing the superpotential up to higher and higher order, but actually solving the critical point equations amounts to solving a set of complicated polynomial equations in multiple variables. And even the best algebraic geometry softwares run out of power very quickly when the number of variables grows. And we have 64 variables in principle here, complex variables. So this seems very hopeless, right? You work very hard and try to lift fields, but you never get close to 36, which is what the tadpole conjecture would say is the bound. And you certainly don't get close to stabilizing all fields, which is 64. Now, shifting gears to the 2 to the 6, where you have a tadpole of 40, 91 moduli. We again start classifying them in terms of the omegas turned on. This will be explained more clearly and more systematically in this paper. If you consider one flux being turned on, there are 3 choices of the vector L that you write down, which I just write down here. Not super important. The point is that 2 of them are physical already. In the 1 to the 9, if you turned on one flux, it was never physical. Turns out here, the tadpole is large enough, it gives you enough space, room to work with, and you get 2 physical solutions already, and you can study higher order terms for these. So you have a flux configuration with 16 n flux, 36 massive fields with nothing getting lifted. And for the other one with 32 n flux and 28 massive fields, you get non-trivial constraints here, but we're simply unable to solve them. So this is different from the 1 to the 9 case. In the 1 to the 9 case, you are either able to solve them and then you truncate at 0 at some point, or you state completely 0 forever. Here you actually get seemingly many non-trivial constraints, but due to our limitations, we just can't make progress there. We can conservatively put down an estimate of what the lower bound here would be, but we refrain from doing this. And the other flux configuration we studied for fun, but it's actually not physical, so it wouldn't have mattered even if you stabilized fields there. Okay, so now what do? We turn on 2 omegas. So everything you see here that goes from G4 to G11 has 2 omegas turned on. Again, not all solutions are physical. You can see some with n flux greater than 40. But since we can exhaustively classify these solutions, we just study them for fun. And you can see where we get 0, we can go all the way up to 6th order in the superpotential. But the places where you actually get non-trivial constraints that might lift fields, we're actually unable to solve the equation. So again, I'm seemingly painting a very depressing story. But let me already point out to you that at the level of the mass matrix rank, this solution is super interesting because it violates this 1/3 bound of the tadpole conjecture. This was found independently by these authors as well, and they have many more such examples, which at the level of the mass matrix rank violates the 1/3 bound. And we heard about this from Mariana as well at string Fino, but it stays within the 1/4 bound, which is the new proposed bound. But yeah, I'll refrain from talking about this. So the next obvious thing for us was to then just look at interesting looking solutions instead of being exhaustive because of our computational abilities. And we came across this one solution from our friends who very graciously let us study it. They found this solution. It has 4 omegas turned on. You have an n flux of 28. It's a physical solution. A mass matrix rank of 75. So this is within the tadpole bound. But then you study higher orders and you can actually lift 9 more fields. And this exactly violates the tadpole conjecture bound. So not only do you see the mass matrix rank violating the 1/3 bound, you can also study higher orders and find the same phenomenon happening. So it's all consistent with the picture that they are uncovering as well. So this is an interesting solution. But the really interesting solutions are these really nasty looking ones with plenty of omegas turned on. So let me again point out one more thing. In the 1 to the 9, I said 1 omega contributes necessarily a flux of 1, an n flux of 1 to the tadpole. And so you can only turn on a maximum of 12 of them. Here this is not true, actually. This feature stops being true. And you can turn on plenty of fluxes. I mean, these are still less than 40 omegas turned on, but still, I'm just making that point. And for both of these, you have n flux 40 and a mass matrix rank of 85. I failed at doing the transition, so the suspense is broken. And you go to higher order and you lift 5 more fields, and you get to 91 fields being stabilized, which is the total number of fields in this model. So this is an isolated supersymmetric Minkowski critical point. Of course, our friends also find much more interesting solutions in the sense that they have n flux equals 40 and full mass matrix rank. So these are completely massive. So of course, they are both isolated critical points, but asking for all fields to be massive is a much harsher constraint than asking for fields to be stabilized. And they even managed to achieve this. And this is all consistent with the tadpole conjecture. So if you naively started out believing in the 1/3 bound, you would have expected this to happen here, potentially. But the claim is very big, so let me also point out the potential caveats. So like it was already mentioned by multiple people, we don't really understand the CFT or whether it's a CFT after deforming by the fluxes. And the arguments for the exactness, the non-perturbative exactness of the superpotential are also not precise, I would say completely. There is evidence, but I don't think it's completely precise. Nevertheless, I still think these models are super interesting and we can find some new phenomena here. Yeah, thank you.